So, good morning, everyone. My name is Vikas Kumar Singh. I am a PhD student at Indian Institute of Science, Bangalore. And in this session, we are going to discuss about the mechanics of sheet metal forming, which course is already there, recorded course is already there on the SWAM website. And this session is designed for live interaction. If you have any doubt in that class, so we can discuss all these things here. And also, we are planning to solve the assignment problem in this session. So coming back to our topic, like mechanics of sheet metal forming. So professor has already discussed so many process and numerical problem concepts and all. So, and he has also designed the design and just made some assignment question so that if you are solving or you are practicing that problem, you will get clarity in your concepts. So I am moving towards the assignments problem first. So we'll see one by one. Okay. So if you will go through the assignments and assignment number 1, which is already released on the website. So I'm just going to solve one by one assignment problem. And if any concept is there in that assignment, which needs to be discussed here, I will discuss that and I will take your queries also. You can ping me on chat box or you can email me. Even in the first slide, email ID was there. You can ask any problem if you have. So we are going to discuss this problem and in the first question, this is given there a low carbon steel rectangular sample of 100 length is elongated to 130 Here we have a rectangular carbon steel block, rectangular carbon steel here, steel rectangular sample of initial length is 100 and it is elongated up to 130 taking the material as isotropic. Okay, so I will discuss what is the meaning of isotropic here so that things will be clear. Find a true strength in length, width, and thickness direction. Okay, by neglecting the elastic deformation. Here we are neglecting the elastic deformation. It means we are talking about plastic deformation only. Okay. So here we have options. We have to choose one out of these 4 options. Okay. So I will just made one rectangular block over here. We have this block. Okay. And this block length is given 100 and some thickness will be there. Like I am just giving some thickness and some width will be there. So this suppose this is going to be in 3D model. This is going to be like this. Okay. So on this face, we have one force and another face we have one force which is pulling this like this. Okay. So this is the length and suppose this is the length and this is the suppose this is the width. I am telling just width W. Okay. And this is the thickness here. So now the question is that isotropic means. So we have a rectangular block means I am just making in 3D block, 3D diagram. So isotropic means all the material properties or in all the direction will be same. Like suppose you have X, Y, Z axis over here like this. This is suppose this X, Y, and Z. And in any direction, in this direction you go, in this direction you go, or in this direction you go, your material property will be same. What does it mean by the material property? Material property means one of the like elastic modulus, Poisson's ratio, bulk modulus. All these properties are same in all the direction. So it's direction independent. It means the isotropic. Okay. Now we have to define the true strain. So if you have gone through the lecture, true strain is nothing but we are defining delta L by L, and this is the integration from L naught to LF. This is the true strain. Okay, true strain, and the final formula is true strain equal to ln of L final by length direction, width direction, and thickness direction. Okay, so length direction easily we can find out because we have LF and LI. So LF will be 130 and divided by 100. Okay, so this one we can find out easily. Now the question is that how to find out that value in width and thickness direction. This is the question, how to find width and thickness direction. So this value will come something, this value will come some, well, if you will solve this problem, this will be ln of 1.3 and this will be 0. Use the scientific calculator, you will get this value. Now, in the plastic deformation, we generally consider volume consistency. Volume. So volume is constant before deformation and after deformation. So volume constant. So this thing we will use volume constant. So whatever volumetric strain is going to be is total 0. So generally we write a strain in length direction plus a strain in width direction plus a strain in thickness direction. The sum of all this will be 0 because volume is constant. So few higher term will also come. If you will derive the formula volumetric strain, some higher terminology will also come that value is very less, close to 0. That generally we ignore that value. So we take only the strain in length, width, and thickness direction. So now we have this value, we don't have this value, and we have to find out. So this value in isotropic material. For isotropic material means E in this direction and E in this direction and E in this direction all are same. So generally for isotropic material, this will be equal to this. So now the formula is going to be epsilon L equal to minus of epsilon W plus epsilon T, and as both are same, so we can write epsilon W equal to epsilon T equal to minus of epsilon L by 2. We can write it like that. Okay, and once we have this value, so we can write it how much? 0.062 divided by 2 and minus sign will be there. So this value is going to come minus of 0.131. So now the point is what does it mean by plus and minus? So plus, it means in one direction, if it is elongating like this, in one direction it is elongating, so another direction it will be shrinking. This thickness will be going like this. So suppose I am just giving one example here. Suppose I am pulling this like this, so this will become something like this. So you can notice this thickness is now this much only. So it means in this direction the strain is negative and in this direction the strain is positive. So here minus sign is coming, means in thickness and width direction, the thickness and width is decreasing and length is increasing. This is called nothing but the volume consistency, means in whatever uh, change in dimension will be there in one direction, other direction will compensate it. Okay, so you can just I'm just giving one general formula for this volume consistency. You can find out like volume, if initial volume is V naught and uh, volume final is Vf. So you can find out volumetric strain Vf minus V naught by V naught. This will be your volumetric strain. And from here, if you will derive this formula, or generally in people are deriving like this also, dV by V equal to volumetric strain. If you will derive this formula, you will get that equation what I wrote. And in this one, you may get a higher order term also, and higher order term is generally neglected because their value is very less comparative to other term in the equation. Okay. So now we are coming to the second question in the assignment first. And this is very interesting question here. A tensile specimen is cut from a metallic sheet of 1.2 mm thickness. 1.2 mm thickness here. The initial gauge width is 12.5 mm and the gauge length is 50 mm. The initial Now, okay, this is the thing. Now I will make one tensile specimen here for your understanding. So let's make one tensile specimen. So tensile specimen is generally made in the shape of dog bone. So this is the gauge length, and here we are generally keeping arc just to avoid the stress concentration. And this is the portion where we are putting this one in the crosshead. I will explain one by one what is crosshead, what is this arc and all. So here we have like this. Okay, so before going to solve this problem, I would like to explain how this testing is done so that it will be clear. So this is the gauge length from here to here. Okay, I am just considering L naught, and thickness is also there. So we can make it like little thicker like this. Okay, and this is going to be something like this, and this is like this. Okay, and we can make it something like this. Okay, this is something like this. Okay, so here we have thickness. Here we have thickness. This is going inside the plate, and that is 1.2 mm. And we have width of 12.5 mm width. Okay, this is the width. I am just considering 12.5 mm here, and length is 50 mm. This one. So generally what is happening, this portion from here to here, this portion is clamped in a cross head. This is clamped. This part is clamped from both sides. From here also, this part is clamped. And we are pulling this in this direction like this with some certain rate. Means what is the crosshead velocity that we will discuss later, that is called a strain rate. So we will apply some load P over here and we'll pull it with some rate. That rate is very important because that is going to come next. What is that called? I will explain a strain rate and all. So we are pulling this. So after certain time, this will fail. And we are putting this cross radius here because just to avoid the stress concentration. If we will sharp edges will be here, so stress will be there, high stress will be there, and because of that high stress, material will fail at that point. But our intention is to fail the material in middle of these 2 point middle. So our intention is here somewhere in this region. So we have to make the sample in such a way material will fail in this region. So for that we need a area which is cross-sectional area which is lower than all the other part. Like here, if you will see cross-sectional area at this point, all are bigger than this, means whatever stress will come at this point will be lower than stress in this region. So that's why we are keeping like this. And this is to avoid the stress concentration. Okay. Now coming to the question A here, the yield load. Yield load is 3 kilonewton, that is P. Extension is 0.07 mm. So determine the initial yield stress. So here I am just writing yield stress equal to P yield point divided by initial area. So this is given 3 kilonewtons. So we can write 3000, and initial area is given. What is that cross sectional area? So cross sectional area over here, it will be this cross section. Okay, this cross section from here, if you will see this, uh, this is the cross section of this thing, like this. Okay, this is the cross section. Okay, so if that cross section is thickness into width. So thickness is how much? 1.2, and width is how much? 12.5. 12.5. So what will be the unit? This is the Newton. This is the Newton, and this is mm square. So it's going to be megapascal. Okay, so we can convert it into gigapascal just by multiplying 10 to the power, just by dividing 10 to the power 3. So, okay, so this term is going to come, if you will do this, this is going to be how much? If you will solve this problem, this is going to be 0.2 into 10 to the power 9. This is going to become like this. And okay, let me solve this. So this will be 3000. Okay, and this will be 3000, and I am just writing here 1.2 into 12.5 into 10 to the power minus 6. Okay, so this is going to be 3 into 10 to the power 9 divided by 1.2 into 12.5, this value. Okay, so if we will take this as a GPA, so this will be 3 by 1.2 into 12.5 GPA. GPA. So this is the GPA value. This is nothing but your yield stress. Okay, yield stress. So if you will convert this, so this, if you will convert this, this is going to become 0.2 GPA, and 0.2 GPA means what? 200 MPa. 200 MPa. So this one will be 200 MPa value. And the next question is asked, when the extension is 15%, the width of the test specimen is 12.4. So initially width was 12.5, and now the width is 11.4. So what determine the R value. So before solving this problem, I would like to explain what is the R value means. Okay, this is very important. What is the R value means? Okay, so coming to R value, R value. So R value is nothing but it is the ratio of strain, true strain, ratio of true strain. The ratio of true strain means which true strain? So generally this is called true strain in the direction of width divided by true strain in the direction of thickness, and this is nothing but R. R value. What is the meaning of this? What is the significance of this? Okay, so generally, I will explain. Generally, when we are doing the sheet metal processing, suppose we have a sheet of thickness T, okay, and we are going to deform it in the cup shape like this. We are going to deform it in the cup shape. So in industry, people generally want to keep this thickness constant, this thickness. So here, whatever thickness is there, same thickness should be here. So but it is not in the actual case. Actual case, the thickness may change. It depends on the material. So how much thickness is going to change, and our intention is keep the thickness as close to as initial case. That is our intention, because if thickness is changed, material may fail because of the thickness reduction. So our intention is to keep that thickness as close to initial case. So suppose this thickness direction strain is low and this is high, it means R value will be greater than 1. So thickness direction strain is low means what? Thickness is not reducing as much as possible. Means thickness reduction is less. So thickness reduction is less. It means we are doing our favorable case. Okay, if thickness value is very high, this value is very high and this is low, it means it is going to be like this R less than 1. R less than 1 is not the favorable case in the industry. People are going with this. So whatever material you are going to use for your sheet metal processing, that R ratio should be greater than 1, and this is desirable for proper forming process. It's clear? Okay. So now the coming to the next point, what is that value, R value? Okay. Okay. Yeah, R value. And one more thing, in the previous question, it was asked here, if you will see, what is the elastic modulus of this thing also. It was asked elastic modulus of this thing also. So elastic modulus, easily we can find out how to find elastic modulus. E equal to sigma by this stress by strain, and we have a strain, yield stress we have found out just in the previous question. Here this value is 200.2 GPa, means 200, here 200 MPa, and we have to find out the strain. And how to find the strain? In the question it is given what? Epsilon extension is given, extension by original length, and extension it is given 0.07 and original length is given 50. So this will be strain, and this value is going to be how much? Whatever, 0.0014. So E will be nothing but your 200 MPa divided by 0.0014. See, generally strain doesn't have any unit, because both this is the change in length, it's unit of length, and this is also length, so unit of length, it will be cancelled. So if we will solve this, we will get 142.85 GPa. Okay, so this is the part of the first question, means A. Now I explained R value to you. R value is strain ratio, true strain ratio in thickness and width direction. And this is nothing but the resistance of thinning of a sheet. Okay, if R value is greater than 1, it's desirable. R value is less than 1, it's not desirable. Okay, so now how to calculate R value? So to calculate R value, we wrote Ln equal to Ln equal to Wf by Wi divided by Ln Tf by Ti. What I am writing this R value equal to? This means what? This is the true strain in width direction, and this is true strain in thickness direction. Okay, so true strain in width direction and true strain in thickness direction. To calculate this value, we need Wf and Wi, and then we need Tf and Ti. Okay, so coming to how to calculate Wf and Wi. So in the question itself, if you will see, it is given like initial, W initial is given, W final is given, and T initial is given, and T final is not given. So how to calculate T final? We have to change, and L initial is given. L initial is given. Okay, L final is also given in term of extension. L final it is saying something. It's in the question itself. It is saying how much? 15% of the extension. Here you can see 15% of the extension. It means L final equal to nothing but 1.15 of L naught. This is 15%. Extension means increase. Okay, this is the L final. This one is given. This one is given how much? L initial, W initial is 12.5. So here this is 12.5. And this one is 11.4, and this one is 1.2, and this one is remaining. So we can calculate how this is happening. Plastic deformation here, and plastic deformation, as we discussed in the initial in the previous problem, like volume consistency will be there. So you can write LIWITI equal to L final, W final, and T final. T final you can write. So from here T final you can calculate just dividing this term by this one. Okay, so we will get the T final from here. So T final will be what? T final equal to, okay, I'm writing T final by T initial. Why? Because T final by T initial value directly we can put it here. So this will be L final, W final divided by L initial, W initial, this value. Okay, now this is nothing but our thickness direction strain, true strain in the thickness direction. Okay, and now similarly we can find in width direction. So width direction ln w, ln w final is what? W final is uh, 12 11.4 and initial is 12.5. So we got this value, this one I also got, and we got T initial by T final by T initial, and T final by T initial, that formula, okay, here it is wrong. Here we have, this term will go down. So here it will come initial and initial, and here it will come final and final. Okay, because what we are taking this terminology here. So this on the nominator, it will be T, L initial and W initial, and denominator L final, W final. So if we will put all this formula here, so we are going to write ln and all value is ln 11.4 by 12.5 and divided by ln, we are going to put 12.5 into 50 and divided by 11.4 into 57.5. 57.5 because this value is going to come 57.5 if we will put here L equal to 50. Okay, so this value is going to come minus 0.092 divided by minus 0.0476. Minus minus will be cancelled, and here we will get 1.93. So you just check this, all this value, because I have already calculated. So directly I am writing all this value. So you can just check all this value. Okay. So this will be the R value. Now you can see here R value is greater than 1. We are getting R equal to 1.93. So whatever sheet material we are using for the forming is desirable. R value is greater than 1. So here it's going to be this value correct, and young modulus we found out this value. Okay. So I hope this is clear. If you have doubt, you can ping me, you can email me. So we can go to next question. So in the next question, you can see here, this is the third problem, and it is given that estimate the strain rate sensitivity index. So before solving this problem, we need to understand what is strain rate sensitivity index. Okay, so if you are aware of a strain rate index, it's very good. Otherwise, I will explain it here. So generally, in the last problem, what we discuss here, I was discussing the loading. There will be some loading rate, means P, how much time it will take to deform this. So that if we are introducing time in the equation, it will this time will introduce one new term in the problem, that is rate. Anything which is time dependent and depends on time, that will give a rate. So here I'm just giving same thing. I'm just drawing it here just to make this thing clear to you. So this was the specimen over here, and we have a here arc with some radius. Okay, like this. Now we are pulling this. This is the tensile testing. Generally, specimens are like this. Okay, this is the gauge length. L naught. Okay. So what is the rate? What is the rate by which we are pulling this? Okay. And this is fixed in a crosshead. This portion is hold, means this is fixed. This part is fixed with some clamp. This is fixed in a clamp that is called crosshead, and that we are pulling this clamp actually, not this thing. This is fixed in the clamp both. Okay. One will be fixed downside and one will be pulled on the top side. So force in the both direction force will be same. Okay, this is fixed and we are pulling. Suppose this is fixed and we are pulling this one in this direction. So this speed of the crosshead, that is velocity, speed of the crosshead with what? Suppose this is fixed here, okay, and we are pulling this. So what is the speed of this crosshead? So if you have remembered, a strain rate was a strain rate is what? If you have a strain equal to what is that strain? Delta L by L, okay, and rate. I am introducing rate. So rate means what? Strain with respect to time, that is rate, and this is denoted by epsilon dot. Okay, so generally people are writing strain rate also d epsilon by dt. This is nothing but strain rate, strain rate. So if this time we are introducing in this one, what will be that? Delta L by L, okay, and divided by time, right? Divided by time. So delta L by T is what? Change in length with respect to time by original length. So change in length by time is nothing but velocity, and velocity by L naught. So a strain rate in terms of velocity, we can write V by L naught. Okay. So this is a strain rate. So uh, in the plastic deformation zone, not linearity is not there. Means in this formula, what you are knowing is applicable in elastic deformation regime, and this formula, like whatever this one is here, this is not, this is called non-linear uh, rule, non-linear law of deformation. And this formula, I am just writing generally written in k into epsilon plus epsilon naught to the power n. This formula is non-linear and it is applicable in plastic deformation. So here plastic deformation is happening and we are not going to use this formula. We can use only this formula. Okay. So here two different kind of strain rate is there. Like V1 and V2 is given 1 mm per second and 20 mm per second. So they're asking strain hardening laws. This is strain hardening laws. Same thing are provided below here. Two laws are given and they're asking find strain rate sensitivity. So this is called strain hardening law. So strain hardening law is in term of strain, and same formula if we are writing in term of a strain rate, so that is called epsilon equal to c into sigma equal to c into epsilon to the power m. Here this was the strain hardening exponent or strain hardening coefficient people are telling, that is n, and here this is called strain rate sensitivity. So m is nothing but strain rate sensitivity. Okay, this is a strain hardening. I'm just writing a strain hardening exponent. Okay, or strain hardening coefficient. So now we have to solve this problem to find out m value. Okay, and this c is constant, k is also constant. So here everything is given. So suppose I have to find out m. What is to be done then? So you can see here to find the m, if we take log in both sides, ln, so this will be, if you will take the log in both sides, so this m will become ln of final by initial divided by ln of epsilon dot final by epsilon dot initial. C will cancel from both sides. Okay, C is a constant, that will be cancelled. So you will get this formula. Okay, just take ln both side and you apply the fundamental formula of logarithmic, you will get this. Okay, so now we have two stress, plastic deformation stress that is given here. Okay, a sigma equal to 500 of this and sigma equal to 530 by this. So you can see this term in the both the stress is same, this term. So this will be cancelled. Only you will have 500 and 530. Okay, so this is going to be 500 by 530. Okay, and now we have to find out strain rate. So how to get the strain rate? So just see this formula just we derived here, V by V naught, sorry, V by L naught. And V by L naught means, suppose I am writing this, so V final by L naught. And if I am writing initial, V initial by L naught. And if I am taking ratio of with the ratio of these two, so L naught, L naught will be cancelled, and we will have V naught, V final by V naught only. So ratio of strain rate will nothing but ratio of velocity. So I am going to write it here, ln V final by V initial, V20 by V1 initial. And if you will put all this value, you will get 0.02. Okay, 0.02. Just solve this problem, you will get this, just cross check. So this is the correct answer for this. I hope this is clear to you. Okay, so now moving to next question. Okay, so I will just take a little more time in power law. So I will explain, it will be clear to you. So see here, I was just discussing here this with what rate we are pulling this crosshead, the velocity of the crosshead. So what is the crosshead? You might be thinking what is the crosshead and how we are pulling and all. So you can think like this. Suppose you have a fixed support here, and you have a beam like this, and this beam is attached with some member, some component like this one. Okay, this is attached with this, and you are pulling this in this direction. You are pulling this direction P. So what is the velocity of this? This is called crosshead. And what is the velocity of this? This velocity is nothing but strain rate. If V by L naught, initial length, if you will divide, so this is nothing but the strain rate. So you can think like this just for your simplicity understanding. Okay. Now, I was just discussing power law, and power law is generally written in terms of sigma. Sometimes people are writing epsilon not here also, and sometimes people are not writing, and this is just the pre-processed strain, means whatever strain is there in the material, or to correct the formula, existing formula. Generally, existing formula is very general, means a standard formula is in term of like this only, but they are introducing this term to generalize the formula. This is called power law, and this power law is applicable in plastic deformation zone. So suppose you have a stress strain curve like this. Okay, like this, and this is failing here. So here you will have ultimate UTS, ultimate tensile stress, and this is, suppose you have yield point Y and this is fracture point. So in this region, this is the elastic deformation. This region is elastic deformation. What is the meaning of linear and non-linear? I'm trying to explain. So this line, this is stress and this is strain. So up to here, this line is linear, and there will be some slope, and that is constant, this slope, and this slope is nothing but E, Young modulus, slope of this line, that is constant. So in this formula, if we have to find out stress, we can apply this formula, stress equal to E into epsilon directly. So this is linear. Okay, how? Because this is in term of Y equal to mx. M is the slope, x is the independent variable, and here x is in term of epsilon. Correct? Now what is happening in this region? So this is non-linear. You can see there is no constant slope. Every point there is one slope. Every point there is a one slope here. So this is not linear zone. This is non-linear. And in this one, the formula is a little modified, and that is called power law. And this is non-linear law in the plastic deformation. So in the plastic deformation, if we have to find out the space, we need this formula. Okay. So this is stress. In term of strain also, this is written in C into epsilon dot into to the power m. Okay, in term of strain rate. And this is also in this zone only, not in this zone. Uh, Not in elastic deformation zone. Both are in plastic deformation zone. Okay. So hope this is clear. Now moving towards the next problem. So again, we have a problem of strain rate sensitivity index M. Same means it's a little bit same question, but we'll see. Here, a sheet of true strain of 0.25 tested at 2 cross head velocity. So I'm just saying two cross head. What does it mean by 2 cross head? That 2 point where that sample was fixed left and right. Okay, velocity in a tensile test, the strain hardening law. Again, I am just I explained the previous slide. Strain hardening is given here. Strain hardening law are provided below. So the tensile tests are done at velocity v1 and v2, and here the law is given, these two. So this is power law. This is called power law. Two different power laws are given. So they are finding a strain rate sensitivity index. So I'm directly writing sensitivity equal to ln because we have already defined this. Okay, and ln strain rate final divided by strain rate initial. Okay. So this is nothing but strain rate sensitivity. So now here formula is little bit modified. Why? Because in the previous problem, if you will remember, it was it was written here something like, here it was written in the term of this plus this not into n. So I told you people are just putting this extra term to generalize the formula to address the previous strain in the material. But generally a standard formula is this. So in the previous problem, if you have noticed the n value was same, means strain hardening exponent or a strain hardening coefficient was same. But here it's they are different. One is 0.2 and one is 0.25. Okay, so they are introducing one extra variable here, n1 and n2. So now when in the previous problem we just divided this divided by this, so we got 500 divided by 550, or in this previous case it was 530, and this was cancelled, this two term was cancelled. But now we cannot cancel because we have n1 and n2. So you can see sigma f by sigma I equal to 500 epsilon to the power 0.2 divided by 550 epsilon to the power 0.25. Okay, so this will be something 500 divided by 550, and here epsilon to the power 0.2 minus 0.25, because this one I am taking on the nominator, so this will become like this, and this is going to be 50 by 55 epsilon to the power minus 0.05. Okay, minus 0.05. So this we can get. Now from where we'll get the epsilon here? So epsilon is already given in the question 0.025. So you can put it directly here and you will get this ratio. And once you will get this ratio, you can put it here directly. So now coming to here, so here nothing is to be done. Same thing like what we did in the previous problem, v initial by v final by v initial, and these two are given 1 and 10. Okay, so I'm just writing you here once again, epsilon dot equal to v by l naught. Also l naught will be cancelled when we are taking the ratio. So we will get this formula. Okay, so this is going to be what? This is going to be, if we are writing, so ln, I'm just writing the whole thing, m equal to ln of 500 ln of what is L final? Okay, here we have made a, here we have written final is this one V2 and initial is this one. So whatever we are writing here, it will be opposite. Okay, because see, we have to write F by this now, and we have written here this. So we can take it opposite way. So take it opposite way. So what will be there? So this will come 500, and here it will be 0.25, and here it will be 0.2. Okay, 20. So this is the top part, and here I'm just correcting it. Here it's whatever I'm writing, I have written this is L final, and here it is L initial. Okay. So and now here ln V final is 10 and V initial is 1. Okay. So if you will solve this, you will get the value of 0.0128. Okay. I have just calculated it. You also, I suggest you calculate, and then you will get it. So in this problem, extra thing was there. They introduced this value, strain value was given, and N1 and N2 was given, N1 and N2. So what is the meaning of N1 and N2? I will explain you this in little detail. So suppose you have a tensile testing of a material, and in X-axis, tensile testing generally X-axis is a strain and this is a stress. So this is elastic zone and this is plastic up to here, and this is, suppose this is plastic zone and here it is fracturing. Okay, so this one corresponds to plastic deformation zone, that is power law non-linear, and this one I am just writing O A B. Okay, and this may be like this may be like this. Okay, so this part, if you are seeing now, this part, this is 1, this is 2, and this is 3, all are different, but up to here it is same. Why? So what is happening in elastic deformation? Elastic deformation, E of a material is constant. Okay, so elastic deformation E is constant. So this part will be same. But in a plastic deformation, hardening or strain rate, hardening exponent may be different, and hardening exponent will depends on with how you are putting the strain in the material, with what rate you are putting the strain in the material, strain rate. What is the strain rate? So according to that, this will vary. So for different n value, this curve will be different. Okay. If n is high, if n is low, it will depends on your hardening rate, with what rate you are putting the strain in the material. So suppose n is 0, what will happen? Suppose n equal to, we are putting k epsilon n. So what will happen if n is 0? It means there is no hardening in the material. Means no hardening means what will happen? Sigma equal to k 0. This one, so sigma equal to k. So sigma will be constant. This will become 1 now. So sigma will be, this will become what? Constant. Suppose sigma is n equal to 1. What will happen? This will become sigma equal to k into this. So see, this is same as the elastic deformation. So in this zone, we are writing sigma equal to E into epsilon, and here we are writing k into epsilon. So it means k and E will be same. So this, when we are putting n equal to 1, it will become elastic deformation. So what I'm trying to say, if n value is something in between 0 and n, you will get some hardening of the material. So what I'm trying to say, you can change n value in the equation, and you can just feel how this equation is changing and relate the equation with that curve, strain stress curve. Then you will get the idea how this n value, what is the business of n, what is the business of epsilon dot and epsilon, all will be clear. Just do some practice and relate it. Basically, you just relate, then you will get the mechanism, how this is happening. N value is 1, n value is 0, n value is in between 0 and 1. So how these are related with the curve, and what is the meaning of hardening, all these things will be clear. Okay, I hope this is clear. So coming to the next question. So here is the next question, and this is same, this is objective question, and this is same what we are discussing from previous two question, strain rate sensitivity and all. So in this question, it is asked what is epsilon in Holloman strain hardening law? Choose the best from the list below. Okay, just read this question and try to figure it out. Already answer is given, but what is that Holloman strain hardening law? This is the point here that I am going to explain. Okay, so what is Holloman strain hardening law? That law is nothing but that power law, what we are discussing from the previous thing, k into epsilon t to the power n. Here, what is happening? Only changes are here we are discussing true stress and true strain. Okay, valid only for this. This is the formula. Okay, for Holloman strain hardening law, same n is the strain hardening exponent or strain hardening coefficient. So this formula is valid only for plastic deformation. Okay. Next, when n equal to 0, what will happen? N equal to 0, what will happen? I just told no hardening. No hardening. Okay. And when n equal to greater than 0 and less than 1, there is hardening. There is hardening in the material. Okay. When n equal to 1, what will happen? Ductile means elastic deformation. N is 1 means elastic deformation only. Na? How? Because n equal to 1 means this will become k into epsilon t. So elastic deformation. Okay. Elastic deformation. So ductile material. Ductile, or you can say elastic deformation. Okay. So I hope this is clear. If you have any doubt, so one more thing I just want to explain you here. In the previous question, whatever we were discussing, this was the elastic zone and this is the plastic zone. So when we are talking about the true stress or strain, so true will always be increasing and this is going to be like this. So this is true stress sigma t and this is engineering stress in plastic deformation. So why this is increasing and why this is decreasing after some time? Why? This is the question that I would like to explain you why this is happening. See, I will just take another slide. Yeah. When we are doing the testing, when we are doing the tensile testing, we have sample like this. Okay, like this. Okay, and when we are pulling this, generally in the case when we are putting in the machine, this is fixed and this was pulled with the crosshead. Okay, this one was pulled. What is happening? Length will increase. Length will increase and it is having some thickness also. So some thickness will be there. Okay, some thickness will be there. So what will happen? Length will increase. Length is going to be something like this. Length will increase, gauge length. Initially gauge length was this much only. Now gauge length is suppose this much only. And width is decreasing. Width is decreasing. Thickness may also decrease. It depends on R value. That initially what we discussed. R value is very high, means more than 1. So change in thickness will be very low. And R value is low, means change in thickness will be there. and that may be considerable. It depends on the R value. So what is happening to the cross-sectional area A naught here? So A naught is W into T. This is the cross-section area. This one, this is the cross-section area. W into T. W is the width and T is the thickness. W into B. W into T. This is the cross-section. So when we are writing stress, formula of stress, we are writing P by A naught or P by A. So P is constant throughout the experiment. We are putting the same P. Okay, but A is changing throughout the experiment. Why A is changing? Because when we are pulling this, area is decreasing, cross-sectional area is decreasing. So suppose at one means suppose cross edge is here, cross edge here, here, means this is moving in this direction. So it may be sigma, this sigma 2 will be P by A2, sigma 3 will be P by A3, like this. It will change, area will change, and change in area will depends on how much length is increasing, and to compensate this increment, length increment, width will decrease. This width will decrease. Okay, there is decrement in the width. So what is happening? Instantaneous area is changing. So I am writing instantaneous AI, or you can write AP, true area. So true area is changing throughout the experiment. So when we are writing true stress, we are writing P by true area. And true area is always decreasing because this is decreasing, W is decreasing, always decreasing. So what will happen? This term is decreasing with the experiment. It means this is in denominator. So it means true stress will increase continuously. So initially we were writing this, and this one was like this. Sorry. Okay. So here this is a constant line, and this is going to be like this. Okay, and so up to here it is increasing, because up to here whatever is happening, that is elastic. And in this region, what is happening in this region, we are taking sigma equal to P by initial stress only, so initial stress, whatever value was there, that is fixed initial stress. Okay, and because of the hardening n, because of the n it may change. Because of the n, the P required to pull this will vary. Means it may be high, it may be low, it depends on, because after some time hardening effect is coming. So when we are talking about the true, so this will continuously increase because our area AT is continuously decreasing. So this is the concept of the true stress and strain, and we'll discuss more about this thing in the coming session. So thing will be clear, and I suggest you go and check. You are remembering all the formula, that is good, but you should know uh, what is the physical meaning of that. That is very important, and how to relate that thing, like hardening. Hardening was there. What is the meaning of hardening? How to address hardening in the stress strain curve? What is the meaning of hardening? Like in the previous slides here, I told three curve here, 1, 2, 3. So for different n value, different curve will be there in the elastic deformation zone, plastic deformation zone. So all these things must be clear, so that whenever you are solving the problem, it will be clear. Okay. So now we'll come to the next question, and next question is again, it's a very simple question. What is the correct unit of true strain rate? Okay, so whatever it's true strain or engineering strain, unit will be same. Okay, so strain rate. Okay, strain rate was nothing but what, like we discussed, strain is delta L by L, and strain rate means we can say this one. Okay, this thing. So we can write it d of delta L by L, and L is constant, L naught we can write, and here dt, and we can write d delta L by dt into 1 by L naught, and this can be V. This is V, velocity, by L naught. So this is strain, this is strain rate. Okay, this is strain rate. So what will be the unit? So V is nothing but meter per second, meter per second. And what is the unit of L naught? Is meter. So meter is cancelled. So it's nothing but per second. Okay. So per second will be the correct answer here. Okay. So this is a very simple question. Okay. So I hope this is clear. You can derive this. Now coming to the next question. In coining and ironing, the sheet is compressed in which direction? So what is the coining and ironing means first? Okay. So what is happening? You have a sheet like this. Suppose you have a sheet of some thickness. Some thickness of sheet is there. And sheet means some length and width will be there. So I'm just considering like this. Okay. So this is the sheet. Coining means you are making a coin out of this seed. So this will be something like this, coining and ironing. So you are punching this seed. Suppose you have a punch of certain diameter here. You are punching this seed to get this coin out of this. Okay. So in which direction we are punching? Always we are punching in thickness direction. Okay, always we are punching in the thickness direction. So see, I will just tell you one thing, like somebody can ask why not in length direction and width direction. So in sheet metal forming, always there is a ratio between L by T or T by L. It depends on with different textbooks. Somebody is writing this, somebody is writing this, or W by T or T by W. There is a ratio, and this ratio is defining you are working with sheet or you are working with a blank of material or you are working with a uh, slab of the material. So sheet means this ratio should be defined, and this ratio, do you know, this is coming from a standard thing like ASTM standard is there for this. What should be the standard? Some book is writing 10, somebody is writing 12, somewhere it is 15. So better you go with the ASTM standard. You will get the exact thing. Like ASTM standard means everybody will follow the same thing. So that is a standard general ratio which is given. So for the if this condition is there, so L is very, very large or W is very, very larger than T. This is nothing but the sheet. So we always punch this along the sheet. Okay. Sheet thickness direction. So thickness direction is nothing but your thickness, winding or ironing process. Okay. So hope this is clear. This is very simple. Now coming to the next problem. Plastic strain ratio of a sheet is defined as, okay, so we have discussed this, and I hope we have solved the problem also. So definitely you will be able to answer this question. This is a ratio of true width strain divided by true thickness strain. That is nothing but what we discuss. R value. R value is what? Plastic strain ratio. Plastic strain ratio. Okay. So plastic strain ratio, and this was a strain ratio of true strain, plastic strain ratio, or you can say plastic true strain ratio of true strain in width direction to uh, true strain in thickness direction. This is the general formula for this, and R value is generally written true strain in which direction, true strain in thickness direction. So true stress, I am writing true strain, sorry, like this. And the physical meaning of this also I explained. Like suppose if you have a sheet of thickness T and you are going to make something, some cup or some any shape, like if you are going to make a shape like this out of this sheet, like this. So thickness uniformity is very important in sheet metal forming. Otherwise, what will happen now? I see at this point you have a stress, high stress because you are bending it here. So what will happen? Sometime material will become like this. I will just give one example to you. Sometime material will become like this, like this. Okay, at this point. So here thickness is reducing. So it's reducing means it will become like this, and after certain time it will fail. The thickness, this will become so thin, this will become so thin, like it will fail at this point, it will break, it will rupture, fracture will be there. So to maintain this thickness throughout the sea, it is very important, this thickness. Okay, so that's why this term is defined R. What should be the R value? So for each and every material, whatever, like it may be aluminum, it may be magnesium, it may be steel, anything, whatever, it may be titanium, whatever sheet metal working you are doing, for each and every material, R value is given. So this value will tell, suppose this is 2, or suppose this is 2.1, or one value is given 1.9. So this value will tell how desirable the process is going to be in terms of thickness reduction. If thickness reduction is very low, so you can form the material, you can deform the material in any shape, and thickness will be uniform throughout the shape. So this is desirable, this is good. Okay, so I hope this is clear. And I think assignment number 1 is finished, and we are going to assignment number 1 is finished, and we are going to solve assignment 2 in the coming session. And if you have any doubt, you can ask in live session, or and I will suggest you also go through all the lecture which is professor is taking, and you just note it down, whatever problem is there in your recorded class, note it down and come here and we can discuss that problem in detail, and you will get clarity in the things concept. Okay, so whatever we have discussed today, all the this thing will be uploaded on YouTube. The link will be shared. You will have access to access this video, and even this PPT, all the PPT will be shared to you. So you can access all this thing. Okay, so the next part is assignment number 2, which we are going to solve in the next Saturday. Saturday 4 to 6 class is there. So all of you can join that class, come live, we will discuss, and we'll sort it out. Whatever problem is there, we'll sort it out. And basically we'll discuss all the fundamental problem here, and fundamental things which you are not getting in the recorded class, whatever professor is discussing. So uh, and also we will discuss some problem other than assignment, whatever in assignment it is there, we can discuss other than that assignment also, so that things will be clear, concept will be clear. Okay, so I request all of you, you can invite your friends also to join this class, and we can discuss. So if attendance is more, so it will be interesting because so many people will be there. They can ask different type of question, so the things will be clear. Okay, so I request, please invite your student friends also and ask them to join. It will be very much interesting, and this is going to be very helpful for your coursework as well as the GATE exam or any other competitive exam which is technical. That is going to be very much important. So please invite. So we'll see you in the next class. Thank you all of you for joining.